In this session, let us learn about breakdown region of a PN junction diode. If you remember, in the previous session, we had drawn this graph of voltage versus current, and the graph looked something like this. And in the previous session we discussed about this region, which was called as saturation region. And now in this session we will discuss about this region, which is called as the breakdown region. Which occurs when the voltage crosses this region called as the breakdown voltage. So the voltage has to keep increasing in negative direction till it crosses this region. So saturation current was in nanoamperes, very small, while this region, current in breakdown region, can be very high in milliamperes or even in amperes. If you remember, in forward bias, a voltage is increased, the current starts increasing only when the voltage crosses the barrier potential. But in reverse bias, the battery voltage supports the barrier potential and keeps increasing the barrier, and this in turn increases the barrier potential. What does it mean, supports? Supports imply that the battery voltage polarity and the barrier potential or the space charge region potential polarity is the same. Once a certain threshold is reached, the ions in the barrier or space charge region are under tremendous pressure. So let us look at the reverse bias condition. Let us draw the picture of a reverse bias diode. This is my P region. This is my N region. And these are positive charges. Those are majority carriers with holes. These are majority carriers, which are electrons. And these are minority carriers, which are electrons. These are minority carriers, which are holes. Now this is the space charge region, and these are ions. These are also positive ions, and this is the barrier voltage. Let's take an example of silicon, in which case it will be 0.6 volts, and its polarity is negative because these are negative ions, and it is positive on this side because these are positive ions. Now let's connect it to a battery. This is the metallic contact or the ohmic contact. This is the battery. So battery polarity is minus and plus. So this is what, when I meant supports, this is what it means. The polarity of both the space charge region and the battery is in the same direction. Thus, it increases the barrier potential, or it increases the space charge region. Now, once a certain threshold of the battery voltage is reached, the ions in the barrier or space charge region, which are under tremendous pressure, these are the ions, can no longer stay there and start hitting at atoms with huge forces. This causes the electrons from atoms to be knocked off from their position and thus creating new electron-hole pairs. So thus, as the battery voltage increases, these ions start moving this side and these ions start moving this side, and they start hitting the atoms here, and they knock off the electrons from these atoms, creating new electron-hole pairs. Electron-hole pairs. Now, the newly formed electrons, which receive huge energy, knocks off these new pairs, knock off neighboring atoms, and thus more electrons are now being created. This process continues, and finally there are many electron-hole pairs causing huge flow of current. So initially the ions go knock off atoms, and electron and hole pairs are created. Now this free electron goes and knocks off electrons from new atoms, and again lot of electrons are created. This goes and knocks off more atoms. All this happens because a lot of energy has been given from this ion to these atoms, and thus this electron hole pair was created, and these atoms send lot more energy and creates new electrons, and thus this creates something called as an avalanche effect. And thus this is called an avalanche diode, and if not controlled, this avalanche effect can actually damage the diode. Now let us look at the Zener breakdown. This requires some knowledge of physics that was studied in the past. Let us draw an energy band gap graph. So this is energy, and this is the material. Let us take the three materials, metal, semiconductor, and the insulator. Let us start with the insulators. So this is insulator. This is for semiconductor. Now this is for metals. This is called as the conduction band, and this is called as the valence band, and this is the band gap. Okay, now consider the band gap, also called as energy gap, as the energy region which is void of any electron states. This gap is very huge for insulators. That means the insulators cannot conduct because they don't have any electron states. And if you look at semiconductors, it is quite small. This region is quite small compared to insulators. But if you look at metals, it actually overlaps, because this is the conduction band and this is the valence band, and it overlaps. In reverse bias, as the barrier potential increases, but before reaching the avalanche breakdown threshold voltage, the voltage could be sufficient for certain electrons to move up from valence band to conduction band. So when the voltage is increased, some electrons can move from here to here, and thus these electrons start moving and cross the barrier. As the reverse voltage increases, this process goes on and results in a huge reverse current. Even though both these breakdowns seem to indicate damage, the diode can be used to our advantage in designing an avalanche diode and a Zener diode. So Zener breakdown happens at low voltages. So Zener breakdown happens at low voltages, like in the range of 5 volts, while avalanche breakdown happens at higher voltages. Avalanche breakdown happens in the range of higher voltages like 100 volts. And thus the Zener diodes operate at lower voltages, while the avalanche diodes operate at higher voltages. And remember, both these voltages are operated in the breakdown region, that is this region. In the next session, let us learn how to mathematically represent the diode under these DC bias conditions, that is forward and reverse bias conditions.